Hello everyone, I am Sumedha. I am from MSc Chemistry first year. Today I am going to read the NCERT chapter. The D and F block elements. Iron, copper, silver and gold are among the transition elements that have played important roles in the development of human civilization. The inner transition elements such as THP and U are proving excellent sources of nuclear energy in modern times. The D block of the periodic table contains the element of the group 3 to 12 in which the d orbitals are progressively filled in each of the four long periods. The F block consists of elements in which 4f and 5f orbitals are progressively filled. They are placed in a separate panel at the bottom of the periodic table. The name transition metals and inner transition metals are often used to refer the elements of D and F blocks respectively. There are main four series of the transition metal: 3D series, 4D series, 5D series and 6D series, which has AC and elements from RF to CN. The two series of the inner transition metals 4F and 5F are known as lanthanoids and actinoids respectively. Originally the name transition metals was derived from the fact that their chemical properties were transitional between those of S and P block elements. Now according to IUPAC, transition metals are defined as metal which have incomplete d subshell either in neutral atom or in their ions. Zinc, cadmium and mercury of group 12 have full D10 configuration in their ground state as well as in their common oxidation state and hence are not regarded as transition metals. However, being the end members of the 3D, 4D and 5D transition series respectively, their chemistry is studied along with the chemistry of transition metals. The presence of partly filled D and D or F orbitals in their atoms make transition elements different from that the ion transition elements. Hence, transition elements and their compounds are studied separately. However, the usual theory of valence as applicable to the non-transition elements can be applied successfully to the transition elements also. Various precious metals such as silver, gold and platinum and industrially important metals like iron, copper and titanium belong to the transition metal series. In this unit we shall first deal with the electronic configuration, occurrence and general characteristic of transition elements with special emphasis on the trend in the property of first row 3D transition metals along with the preparation and properties of some important compound. This will be followed by consideration of certain general aspects such as electronic configuration, oxidation, physical chemical reactivity of the inner transition metal. The transition elements D block. Position in the periodic table. The D block occupies the large middle section of the periodic table flanked between S and P blocks in the periodic table. The D orbitals of the penultimate energy levels of atoms received electrons, giving rise to four rows of the transition metals. For example, 3D, 4D, 5D and 6D. All these series of transition elements are shown in table 4.1. Electronic configuration of the D block elements. In general, the electronic configuration of outer orbitals of these elements is n-1, d1 10, ns1 2, except for PD where its electronic configuration is 4d10 5s0. The n-1 stands for the inner d orbitals which may have 1 to 10 electrons and the outermost ns orbital may have 1 or 2 electrons. However, this generalization has special exceptions because of very little energy difference between n-1d and ns orbitals. Furthermore, half and completely filled sets of orbitals are relatively more stable. A consequence of this factor is reflected in the electronic configurations of chromium and copper in 3D series. For example, Consider the case of chromium, which has 3d5,4s1 configuration instead of 3d4,4s2. The energy gap between the two set 3d and 4s of orbitals is small enough to prevent electron entering the 3d orbitals. Similarly, in case of copper, the configuration is 3d10,4s1 and not 3d9,4s2. The ground state electronic configuration of outer orbitals of transition elements are given in table 4.1. The electronic configuration of outer orbitals of Zn, Cd, Hg and Cn are represented by the general formula n-1d10 ns2. The orbitals in these elements are completely filled in the ground state as well as in their common oxidation states. Therefore, they are not regarded as transition elements. The d orbital of the transition elements protrude to the periphery of an atom more than the other orbitals, i.e. s and p. Hence, they are more influenced by surrounding as well as affect the atom or molecule surrounding them in some respects. Ions of a given Dn configuration n is equal to 1 minus 9 have similar magnetic and electronic properties with partly filled d orbitals. These elements exhibit certain characteristic properties such as display of a variety of oxidation states, formation of colored ions, and entering into complex formation with a variety of ligands. The transition metal and their compounds also exhibit catalytic property and paramagnetic behavior. All these characteristics have been discussed in detail later in this unit. There are greater similarities in the properties of transition elements of a horizontal row in contrast to the non-transition elements. However, some group similarities also exist. We shall first study the general characteristics and their trends in the horizontal rows, particularly 3D row, and then consider same group similarities. On what ground can you say that scandium is a transition element but zinc is not? On the basis of incompletely filled 3D orbitals in case of scandium atom in its ground state 3D1, it is regarded as a transition element. On the other hand, zinc atom has completely filled d orbitals 3D10 in its ground state as well as in its oxidized state, hence it is not regarded as transition element. We will discuss the properties of elements of first transition series only in following sections. Physical properties. General properties of the transition elements D block. Nearly all the transition elements display typically metallic properties such as high tensile strength, ductility, malleability, high thermal and electrical conductivity, and metallic luster. With the exceptions of zinc, Cd, Hg and Mn, they have one or more typical metallic structures at the normal temperatures. The transition metals, with the exception of zinc, Cd and Hg, they are very hard and have low volatility. Their melting and boiling points are high. Figure 4.1 depicts the melting point of transition element belonging to 3D, 4D and 5D series. The high melting points of these metals are attributed to the involvement of greater number of electrons from n-1d in the addition to the ns electron in the interatomic metallic bonding in any row. The melting point of these metals rise to a maximum at D5 except for anomalous values of Mn and Tc and falls regularly as the atomic number increases. They have high enthalpies of atomization which are shown in figure 4.2. The maxima at about the middle of each series indicate that one unpaired electron per d orbital is particularly favorable for strong interatomic interaction. In general, greater the number of valence electrons, stronger is the resultant bonding. Since the enthalpy of atomization is an important factor in determining the standard electrode potential of a metals with very high enthalpy of atomization, i.e. very high boiling point, tend to be noble in their reactions. See later for electrode potentials. Another generalization that may be drawn from figure 4.2 is that the metals of the second and third series have greater enthalpies of atomization than the corresponding elements of the first series. This is an important factor in accounting for the occurrence of much more frequent metal-metal bonding in compounds of the heavy transition metals. Variation in the atomic and ionic sizes of transition metals. In general, ions of the same charge in a given series show progressive decrease in the radius with increasing atomic number. This is because the new electron enters a d orbital each time the nuclear charge increases by unity. It may be recalled that the shielding effect of a d electron is not that effective, hence the net electrostatic attraction between the nuclear charge and the outermost electron increases and the ionic radius decreases. The same trend is observed in the atomic radii of a given series. However, the variation within a series is quite small. An interesting point emerges when atomic sizes of one series are compared with those of the corresponding elements in other series. The curve in figure 4.3 shows an increase from the first 3D to second 4D series of the elements, but the radii of the third 5D series are virtually the same as those of the corresponding member of second series. This phenomena is associated with the intervention of 4f orbitals, which must be filled before the 5d series of elements begin. The filling of 4f before 5d orbitals result in a regular decrease in atomic radii called lengthened contraction, which essentially compensate for the expected increase in atomic size with increasing atomic number. The net result of the lengthened contraction is that the second and the third D series exhibit similar radii and have very similar physical and chemical properties, much more than the expected on the basis of usual family relationship. The factor responsible for the lengthened contraction is somewhat similar to that observed in any ordinary transition series and is attributed to similar cause. The imperfection shielding of one electron by another in the same set of orbitals. However, the shielding of one 4f electrons by another is less than that of one d electron by another. And as the nuclear charge increases along the series, there is fairly regular decrease in the size of entire 4fn orbitals. The decrease in metallic radii coupled with the increase in atomic mass result in a general increase in density of these elements. Thus, from titanium Z is equal to 22 to copper Z is equal to 29, the significant increase in the density may be noted. Table 4.2. Ionization enthalpies. There is an increase in ionization enthalpy along each series of the transition element from left to right due to an increase in nuclear charge which accompanies the filling of the inner d orbitals. Tables 4.2 give the values of first three ionization enthalpies of the first series of transition elements. These values show that the successive enthalpies of these elements do not increase as steeply as in the case of non-transition element. The variation in ionization enthalpy along a series of transition elements is much less in comparison to the variation along a period of non-transition elements. The first ionization enthalpy in general increases, but the magnitude of the increase in the second and third ionization enthalpies for the successive elements is much higher along a series. The irregular trend in the first ionization enthalpy of the metal of 3D series, though of little chemical significance, can be accounted for by considering that the removal of one electron alters the relative energies of 4s and 3D orbitals. You have learned that when d block elements form ions, ns electrons are lost before n-1 d electrons. As we move along the period in 3D series, we see that nuclear charge increases from scandium to zinc, but electrons are added to the orbitals of inner subshell, i.e. 3D orbitals. These 3D electrons shield the 4s electrons from the increasing nuclear charge somewhat more effectively than the outer shell electrons can shield one another. Therefore, the atomic radii decrease less rapidly, thus ionization energies increase only slightly along the 3D series. The W or more highly charged ions have DN configuration with no 4s electrons. A general trend of increasing values of second ionization enthalpy is expected as the effective nuclear charge increases, because one d electron does not shield another electron from the influence of nuclear charge, because d orbitals differ in direction. However, the trend of steady increase in second and third ionization enthalpy breaks for the formation of Mn2 positive and Fe3 positive respectively. In both the cases, ions have d5 configuration. Similar breaks occur at corresponding elements in the later transition series. The interpretation of variation in ionization enthalpy for an electronic configuration Dn is as follows. The three terms responsible for the value of ionization enthalpy are attraction of each electron towards nucleus, repulsion between the electrons, and exchange energy. Exchange energy is responsible for the stabilization of energy state. Exchange energy is approximately proportional to the total number of possible pair of parallel spins in the degenerate orbitals. When several electrons occupy a set of degenerate orbitals, the lowest energy state corresponds to the maximum possible extent of single occupation of orbital and parallel spins. Hund's rule. The loss of exchange energy increases the stability. As the stability increases, the ionization becomes more difficult. There is no loss of exchange energy at d6 configuration. Mn positive has 3d5 4s1 configuration, and configuration of Cr positive is d5. Therefore, ionization enthalpy of Mn positive is lower than Cr positive. In the same way, Fe2 positive has d6 configuration and Mn2 positive has 3d5 configuration. Hence ionization enthalpy of Fe2 positive is lower than the Mn2 positive. In other words, we can say that the third ionization enthalpy of Fe is lower than that of Mn. The lowest common oxidation state of these metals is +2 to form the Mn2 positive ions from the gaseous atom. The sum of the first and second ionization enthalpy is required in the addition to the enthalpy of atomization. The dominant term is the second ionization enthalpy, which shows usually high values for chromium and copper, where M positive ions have the d5 and d10 configuration respectively. The value for Zn is correspondingly low, as the ionization causes the removal of one 4s electron, which result in the formation of stable d10 configuration. The trend in the third ionization enthalpies is not complicated by the 4s orbital factor and shows the greater difficulty of removing an electron from the d5 Mn2 positive and d10 Zn2 positive ion. In general, the third ionization enthalpies are quite high. Also, the high values for third ionization enthalpy of copper, nickel, and zinc indicate why it is difficult to obtain oxidation state greater than 2 for these elements. Although ionization enthalpies give some guidance concerning the relative stabilities of oxidation state, this problem is very complex and non-amenable to ready generalization. Oxidation state. One of the notable features of a transition element is great variety of oxidation states. These may show in their compounds. Table 4.3 lists the common oxidation states of the first row transition elements. The elements which give the greatest number of oxidation state occur in or near the middle of the series. Manganese, for example, exhibit all the oxidation state from +2 to +7. The lesser number of oxidation state at the extreme end stems from either too few electrons to lose or share scandium, titanium, or too many d electrons, hence fewer orbitals available in which to share electrons with other. For higher valence copper, zinc, thus early in the series, scandium is virtually unknown and titanium is more stable than Ti third or Ti second. At the other end, the only oxidation state of zinc is +2. No d electrons are involved. The maximum oxidation state of reasonable stability corresponds in the value of the sum of the s and d orbital electrons up to manganese, followed by rather abrupt decrease in stability of higher oxidation state, so that the typical species to follow are Fe23, CO23, Ni2, Cu1 and 2, Zn2. The variability of oxidation states, a characteristic of transition elements, arises out of incomplete filling of d orbitals in such a way that their oxidation state differ from each other by unity. For example, V2, V3, V4 and V5. This is in contrast with the variability of oxidation state of non-transition elements, where oxidation states normally differ by a unit of 2. An interesting feature is in the variability of oxidation states of the d block elements is noticed among the group 4 through 10. Although in p block the lower oxidation states are favored by the heavier members due to inert pair effect, the opposite is true in the groups of D block. For example, in group 6, MO6 and W6 are found to be more stable than Cr6. Thus, Cr6 in the form of dichromate in acidic medium is a strong oxidizing agent, whereas MO3 and WO3 are not. Low oxidation states are found when a complex compound has ligands capable of pi acceptor character in addition to the sigma bonding. For example, in NiCO4 and FeCO5, the oxidation state of nickel and iron is 0. Trends in the M2 positive and M standard electrode potential. Table 4.4 contains the thermochemical parameters related to the transformation of the solid metal atoms to M and 2 positive ions in solution and their standard electrode potential. The observed value of E negative and those calculated using the data of table 4.4 are compared in figure 4.4. The unique behavior of Cu having a positive E negative accounts for its inability to liberate hydrogen from acids. Only oxidizing acids, nitric acid and hot concentrated sulfuric, react with Cu. The acid being reduced the high energy to transform Cu to Cu2 positive is not balanced by its hydration enthalpy. The general trend towards less negative E minus values across the series is related to the general increase in the sum of the first and second ionization enthalpy. It is interesting to note that the value of E negative for Mn, Ni and Zn are more negative than expected from the trend. The stability of half-filled D subshell in Mn2 positive and the completely filled D10 configuration in Zn2 positive are related to their E naught values, whereas E naught for Ni is related to the highest negative delta hydration H naught. Trends in the M3 positive, M2 positive standard electrode potential. An examination of the E naught, M3 positive and M2 positive values. Table 4.2 shows the varying trends. The low value for Sc reflect the stability of Sc3 positive, which has a noble gas configuration. The highest value of Zn is due to the removal of an electron from the stable D10 or configuration of Zn2 positive. The comparatively high value for Mn shows that Mn2 positive D5 is particularly stable, whereas comparatively low value for Fe shows the extra stability of Fe3 positive D5. The comparatively low value for V is related to the stability of V2 positive half-filled T2G unit level. Unit 5. Trends in the stability of higher oxidation state. Table 4.5 shows the stable halides of the third series of transition metals. The highest oxidation number are achieved in TiX4 tetrahalides, VF5 in and CrF6. The +7 state for Mn is not represented in simple halides, but Mn3O3F is known, and beyond Mn no metal has a trihalide except FeX3 and COF3. The ability of fluorine to stabilize the highest oxidation state is due to either higher lattice energy, as the case of COF3, the higher bond enthalpy terms for the higher covalent compounds, e.g. VF5 and CRF6. Although V plus 5 is represented only by VF5, the other halides, however, undergo hydrolysis to give oxohalides. VOX3. Another feature of fluorides is their instability in the low oxidation state, e.g. VX2, and the same applies to CuX. On the other hand, all Cu2 halides are known except the iodide. In this case, Cu2 positive oxide I negative to I2. However, many copper compounds are unstable in aqueous solution and undergo dispersion. The stability of Cu2 positive rather than Cu positive is due to much more negative dehydration H naught of Cu2 positive than Cu positive, which more than compensate for the second ionization enthalpy of Cu. The ability of oxygen to stabilize the highest oxidation state is demonstrated in the oxides. The highest oxidation number in the oxides coincide with the group number and is attained in Sc2O3 to Mn2O7. Beyond group 7, no higher oxides of Fe above Fe2O3 are known. Although ferrates are formed in alkaline media, but they readily decompose to Fe2O3 and O2. Besides the oxides, oxocations stabilize Vv as VO2 positive, V4 as VO2 positive, and Ti4 as TiO2 positive. The ability of oxygen to stabilize these high oxidation state exceed that of fluorine. Thus, the highest Mn fluoride is MnF4, whereas the highest oxide is Mn2O7. The ability of oxygen to form multiple bonds to metals explain its superiority. In the covalent oxide Mn2O7, each Mn is tetrahedrally surrounded by O's, including a MnO-Mn bridge. The tetrahedral MO4 N negative ions are known for V5 Cr6 Mn5 Mn6 and Mn7. Chemical reactivity and E naught values. Transition metals vary widely in their chemical reactivity. Many of them are sufficiently electropositive to dissolve in mineral acids, although a few are noble, that is, they are unaffected by single acids. The metal of the first series, with the exception of copper, are relatively more reactive and are oxidized by 1 Mh positive, though the actual rate at which these metals react with oxidizing agent like hydrogen ion is sometimes slow. For example, titanium and vanadium in practice are passive to dilute non-oxidizing acid at room temperature. The E naught values for M2 positive and M indicate a decreasing tendency to form divalent cations across the series. This general trend towards less negative E naught values is related to the increase in the sum of the first and second ionization enthalpies. It is interesting to note that the E naught values for Mn, Ni and Zn are more negative than expected from the general trend, whereas the stabilities of half-filled d subshell d5 in Mn2 positive and completely filled d subshell d10 in zinc and are related to their E values. For nickel, E naught values is related to the highest negative enthalpy for hydration. An examination of the E naught values for the redox couple M3 positive M2 positive table 4.2 shows that Mn3 positive and CO3 positive ions are the strongest oxidizing agents in aqueous solution. The ions Ti2 positive and V2 positive and Cr2 positive are strong reducing agents and will liberate hydrogen from a dilute acid. 2 Cr2 positive aqueous plus 2 H positive gives 2 Cr3 positive plus H2. Magnetic properties. When a magnetic field is applied to the substance, mainly two types of magnetic behavior are observed: diamagnetism and paramagnetism. Diamagnetic substances are repelled by the applied field, while the paramagnetic substances are attracted. Substances which are attracted very strongly are said to be ferromagnetic. In fact, ferromagnetism is an extreme form of paramagnetism. Many of the transition metal ions are paramagnetic. Paramagnetism arises from the presence of unpaired electron, each such electron having a magnetic moment associated with its spin angular momentum and orbital angular momentum. For the compound of the first series of transition metal, the contribution of the orbital angular momentum is effectively quenched and hence is of no significance. For these, the magnetic moment is determined by the number of unpaired electrons and is calculated by using spin only formula, i.e. mu is equal to n into n plus 2 under root, where n is the number of unpaired electrons and mu is the magnetic moment in units of Bohr magneton. Bm, a single unpaired electron has a magnetic moment of 1.73 Bohr magnetons. The magnetic moment increases with the increasing number of the unpaired electrons. Thus, the observed magnetic moment gives a useful indication about the number of unpaired electrons present in an atom, molecule or ion. The magnetic moments calculated from the spin-only formula and those derived experimentally for some ions of the first row transition elements are given in table 4.7. The experimental data are mainly for hydrated ion in solution or in the solid state. Formation of colored ions. When an electron from a lower energy d orbital is excited to a higher energy d orbital, the energy of excitation corresponds to the frequency of light absorbed. Unit 5. This frequency generally lies in the visible region. The color observed corresponds to the complementary color of a light absorbed. The frequency of the light absorbed is determined by the nature of the ligand. In aqueous solution, where water molecules are the ligands, the colors of the ions observed are listed in table 4.8. A few colored solution of D block elements are illustrated in figure 4.5. Formation of complex compounds. Complex compounds are those in which the metal ions binds a number of anions or neutral molecules, giving complex species with characteristic properties. A few examples are FeCN6 3 negative, FeCN6 4 negative, CuNH3 2 positive, and PtCl4 2 negative. The chemistry of complex compound is dealt with in detail in Unit 5. The transition metals from a large number of complex compounds. This is due to the comparatively smaller size of the metal ions, their high ionic charges, and the availability of d orbitals for bond formation. Catalytic properties. The transition metal and their compounds are known for their catalytic activity. This activity is ascribed to their ability to adopt multiple oxidation states and to form complexes. Vanadium oxide in contract process, finely divided iron in Haber's process, and nickel in catalytic hydrogenation are some of the example. Catalysts at a solid surface involve the formation of bonds between reactant molecule and atom of the surface of the catalyst. First row transition metal utilize 3d and 4s electrons for bonding. This has the effect of increasing the concentration of the reactants at the catalyst surface and also weakening of the bonds in the reacting molecule, for the activation energy is lowering. Also, because the transition metal ions can change their oxidation states, they become more effective as catalysts. For example, iron 3 catalyzes the reaction between iodide and persulfate ions. 2I negative plus S2O8 2 negative gives I2 plus 2SO4 2 negative. An explanation of this catalytic action can be given as 2Fe3 positive plus 2I negative gives 2Fe2 positive plus 2I2. 2Fe2 positive plus 2S2O8 2 negative gives 2Fe3 positive plus 2SO4 2 negative. Formation of interstitial compounds. Interstitial compounds are those which are formed when the small atoms like hydrogen, carbon and nitrogen are trapped inside the crystal lattice of metal. They are usually non-stoichiometric and are neither typically ionic nor covalent. For example, TiCmN4N Fe3H VHO VH 0.56 and TiH 1.7 etc. The formulas quoted do not of course correspond to the normal oxidation state of the metal because of the nature of their composition. These compounds are referred to as interstitial compounds. The principal physical and chemical characteristics of these compounds are as follows. They have high melting points, higher than those of pure metals. They are very hard. Some borides approach diamonds in hardness. They retain metallic conductivity. They are chemically inert. Alloy formation. An alloy is a blend of metals prepared by mixing the components. Alloy may be homogeneous solid solution in which the atoms of one metal are distributed randomly among the atoms of the other. Such alloys are formed by atoms with metallic radii that are within about 15% of each other because of similar radii and other characteristics of transition metal. Alloys are readily formed by these metals. The alloys of so formed are hard and have often high melting points. The best known are ferrous alloys. Chromium, vanadium, tungsten, molybdenum and manganese are used for the production of a variety of steel and stainless steel alloy of transition metals. With non-transition metals such as brass, copper, zinc, bronze, copper, tin are also of considerable industrial importance. Some important compounds of transition elements: oxide and oxygens of metals. These oxides are generally formed by the reaction of metals with oxygen at high temperature. All the metals except scandium forms MO oxides which are ionic. The highest oxidation number in the oxides coincide with the group number and is attained in Sc2O3 to Mn2O7. Beyond group 7, no higher oxides of iron above Fe2O3 and are known. Besides the oxides, the oxocations stabilize V5 as VO2 positive and V4 as VO2 positive and Ti4 as TiO2 positive. As the oxidation number of a metal increases, the ionic character decreases. In the case of Mn2O7 is a covalent green oil. Even CrO3 and V2O5 have low melting points. In these higher oxides, the acidic character is predominant. Thus, Mn2O7 gives HMnO4 and CrO3 gives H2CrO4 and H2Cr2O7. V2O5 is however amphoteric throughout, mainly acidic, and it gives VO4 3 negative as well as VO2 positive salts. In vanadium, there is a gradual change from the basic V2O3 to less basic V2O4 and to amphoteric V2O5. V2O4 dissolved in the acid to give VO2 positive salt. Similarly, V2O5 react with alkalis as well as acid to give VO4 3 negative and VO4 positive respectively. The well characterized CRO is based, but Cr2O3 is amphoteric. Potassium dichromate K2Cr2O7. Potassium dichromate is a very important chemical used in leather industry and is as an oxidant for preparation of many azo compounds. Dichromates are generally prepared for chromate, which in turn are obtained by the fusion of chromite or FeCr2O4 with sodium or potassium carbonate in free access of air. The reaction with sodium carbonate occurs as follows: 4 FeCr2O4 plus 8 Na2CO3 plus 7 O2 gives 8 Na2CrO4 plus 2 Fe2O3 plus 8 CO2. The yellow solution of sodium chromate is filled and acidified with sulfuric acid to give a solution from which orange sodium dichromate Na2Cr2O7.2H2O can be crystallized. 2 Na2CrO4 plus 2H positive gives Na2Cr2O7 plus 2 Na positive plus H2O. Sodium dichromate is more soluble than potassium dichromate. The latter is therefore prepared by treating the solution of sodium dichromate with potassium chloride. Na2Cr2O7 plus 2 KCl gives K2Cr2O7 plus 2 NaCl. Orange crystal of potassium dichromate crystallize out. The chromates and dichromates are interconvertible in aqueous solution depending upon pH of the solution. The oxidation state of chromium in chromate and dichromate is the same. 2Cr CrO4 2 negative plus 2H positive gives Cr2O7 2 negative plus H2O. Cr2O7 2 negative plus 2OH negative gives 2CrO4 2 negative plus H2. The structures of the chromate ion CrO4 2 negative and the dichromate ion Cr2O7 2 negative are shown below. The chromate ion is tetrahedral, whereas the dichromate ion consists of two tetrahedral sharing one corner with CrO-Cr bond angle of 126 degree. Sodium and potassium dichromates are strong oxidizing agents. The sodium salt has a greater solubility in water and is extensively used as an oxidizing agent in organic chemistry. Potassium dichromate is used as a primary standard in volumetric analysis in acidic solution. Its oxidizing action can be represented as follows: Cr2O7 2 negative plus 14H positive plus 6 electrons gives 2 Cr3 positive plus 7H2O. E naught is equal to 1.33 V. Thus, acidified potassium dichromate will oxidize iodides to iodine, sulfides to sulfur, tin 2 to tin 4, and iron second, salts to iron third. The half reactions are noted below. 6I negative gives 3I2 plus 6 electrons. 3H2S gives 6H positive plus 3S plus 6 electrons. The fully ionic equation may be obtained by adding the half reaction for the potassium dichromate to the half reaction for the reducing agent. For example, Cr2O7 2 negative plus 14H positive plus 6 Fe2 positive gives 2 Cr3 positive plus 6 Fe3 positive plus 7H2. Potassium permanganate KMnO4. Potassium permanganate is prepared by fusion of Mn2O2 with an alkali metal hydroxide and oxidizing agent like KNO3. This produces the dark green K2MnO4, which disproportionates in a neutral or acidic solution to give permanganate. 2MnO2 plus 4KOH plus O2 gives to 2K2MnO4 plus 2H2O. 3MnO4 2 negative plus 4H positive gives to 2MnO4 negative plus MnO2 plus 2H2O. Commercially, it is prepared by the alkaline oxidative fusion of MnO2 followed by the electrolytic oxidation of manganate. MnO2 fused with KOH oxidized with air or KNO3 gives MnO4 2 negative manganate ion. MnO4 2 negative manganate electrolytic oxidation in alkaline solution gives MnO4 negative permanganate ion. In the laboratory, a manganese 2 ion salt is oxidized by peroxo disulfate to permanganate 2 Mn2 positive plus 5S2O8 2 negative plus 8H2O gives 2 MnO4 negative plus 10SO4 2 negative plus 16H positive. Potassium permanganate forms dark purple, almost black crystal which are isostructural with those of KClO4. The salt is not soluble in water, but when heated it decomposes at 513 Kelvin. 2KMnO4 gives 2K2MnO4 plus MnO2 plus O2. It has two physical properties of considerable interest: its intense color and its diamagnetism along the temperature dependent weak paramagnetism. These can be explained by the use of molecular orbital theory, which is beyond the present scope. The manganate and permanganate ions are tetrahedral. The pi bonding takes place by overlap of p orbitals of oxygen and with d orbitals of manganese. The green magnet is paramagnetic because of one unpaired electron, but the permanganate is diamagnetic due to the absence of unpaired electron. Acidified permanganate solution oxalates to carbon dioxide, iron 2 to iron 3, nitrates to nitrates, and iodides to free iodine. The half reaction of reductants are 5 Fe2 positive gives 5 Fe3 positive plus 5 electron. 5 NO2 negative plus 5 H2O gives 5 NO3 negative plus 10 H positive plus 10 electron. The full reaction can be written by adding the half reaction for KMnO4 to the half reaction of a reducing agent, balancing wherever necessary. If we present the reduction of permanganate to manganese dioxide and manganese second salt by half reactions. MnO4 negative plus electron gives MnO4 2 negative. MnO4 negative plus 4H positive plus 3 electron gives MnO2 plus 2H2O. We can very well see that the hydrogen ion concentration of the solution plays an important part in influencing the reaction. Although many reactions can be understood by consideration of redox potential, kinetics of the reaction is also an important factor. Permanganate at H positive is equal to 1 should oxidize water, but in practice the reaction is extremely slow unless either manganese 2 ions are present or temperature is raised. A few important oxidizing reactions of KMnO4 are given below. In acid solution, iodine is liberated from potassium iodide. Fe2 positive ion green is converted to Fe3 positive yellow. Oxalate ion or oxalic acid is oxidized at 333 Kelvin. Hydrogen sulfide is oxidized, sulfur being precipitated. Sulfurous acid or sulfite is oxidized to a sulfate or sulfuric acid. Nitrite is oxidized to nitrate. In neutral or faintly alkaline solution, a notable reaction is the oxidation of iodide to iodate. Thiosulfate is oxidized almost quantitatively to sulfate. Manganous salt is oxidized to MnO2. The presence of zinc sulfate of zinc oxide catalyzes the oxidation. Permanganate titration in presence of hydrochloric acid are unsatisfactory since hydrochloric acid is oxidized to chlorine. Besides it's in analytical chemistry, potassium permanganate is used as a favorite oxidant in preparative organic chemistry. Its uses for the bleaching of wool, cotton, silk and other textile fibers and for the decolorization of oils are also dependent on its strong oxidizing power. The inner transition elements F block. The F block consists of two series lanthanoids, the 14 elements following lanthanum, and actinoids, the 14 elements following actinum. Because lanthanum closely resembles the lanthanoids, it is usually included in any discussion of the lanthanoids for which the journal symbol An is often used. Similarly, a discussion of the actinoids includes actinum besides the 14 elements constituting the series. The lanthanoids resemble one another more closely than to the members of ordinary transition elements in any series. They have only one stable oxidation state and their chemistry provides an excellent opportunity to examine the effect of small changes in size and nuclear charge along a series of otherwise similar elements. The chemistry of the actinides is, on the other hand, much more complicated. The complication arises partly owing to the occurrence of a wide range of oxidation states in these elements and partly because their radioactivity creates special problems in their study. The two series will be considered separately here. The lanthanoids, the name symbols electronic configuration of atomic and some ionic states and atomic and ionic radii of lanthanum and lanthanoids for which the general symbol N is used, given in table 4.9. Electronic configuration. It may be noted that the atoms of these elements have electronic configuration with 6s2 common with a variable occupancy of 4f level ions. However, the electronic configuration of the tripositive ions, the most stable oxidation state of the lanthanoids, are of the form 4Fn. N is equal to 1 to 14 with increasing atomic number. Atomic and ionic sizes. The overall decrease in the atomic and ionic radii from lanthanum to lutetium, the lanthanide contraction, is a unique feature in the chemistry of the lanthanoids. It has far-reaching consequences in the chemistry of the third transition series of elements. The decrease in atomic radii derived from the structure of metals is not quite regular as it is regular in Mn3 positive ions. This contraction is of course similarly to that observed in an ordinary transition series and is attributed to the same cause, the information shielding of one electron by another in the same subshell. However, the shielding of one 4 electron by another is less than 1 d electron by another. With the increase in nuclear charge around the series, there is fairly regular decrease in the sizes with increasing atomic number. The cumulative effect of the contraction of the lanthanoid series, known as lanthanoid contraction, cause the radii of the members of the third transition series is to very similar to those of corresponding members of the second series. The almost identical radii of Z are 160 pm and HF 159 pm. A consequence of the lanthanide contraction account for their occurrence together in nature for the difficulty faced in their separation. Oxidation state in the lanthanides Li2 and Ln3 compounds are predominant species. However, occasionally +2 and +4 ions in solution or in solids compounds are obtained. This irregularity, as in ionization enthalpies, arises mainly from the extra stability of empty half-filled or filled F subshell. Thus, the formation of Ce4 is favored by its noble gas configuration, but it is strong oxidant reverting to the common +3 state. The E0 value for Ce4 positive C and C3 positive is plus 1.74 V, which suggests that it can oxidize water. However, the reaction rate is very slow and hence Ce4 is a good analytical reagent. PR, ND, TB and DY also exhibit +4 state but only in oxides. MO2 EU2 positive is formed by losing the 2 electrons, S electrons, and its F7 configuration account for the formation of this ion. However, U2 positive is a strong reducing agent, changing to the common +3 state. Similarly, YB2 positive, which has F14 configuration, is a reductant. TB4 has a half-filled F orbitals and is an oxidant. The behavior of samarium is very much like europium, exhibit both +2 and +3 oxidation state. General characteristic: all the lanthanoids are silvery white soft metal and tarnish rapidly in air. The hardness increases with increasing atomic numbers. Samarium being steel hard, their melting points range between 1000 to 1200 Kelvin, but samarium melts at 1623 Kelvin. They have typical metallic structure and they are good conductors of heat and electricity, density and other properties change smoothly except for EU and YB and occasionally for SM and TM. Many trivalent lanthanoid ions are colored both in solid state and in aqueous solution. Color of these ions may be attributed to the presence of the F electrons. Neither Li3 positive nor Lu3 positive ion shows any color, but the rest do so. However, absorption bands are narrow, probably because of the excitation within F level. The lanthanide ions other than the F0 type Li3 positive and Ce4 positive and the F14 type YB2 positive and Lu3 positive are all paramagnetic. The first ionization enthalpy of the lanthanoids are around 600 kilojoule mole inverse. The second about 1200 kilojoule mole inverse, comparable with those of calcium. A detailed discussion of the variation of the third ionization enthalpy indicates that the exchange enthalpy concentration as in 3d orbitals of the first transition metal appear to impact a certain degree of stability to empty, half-filled and completely filled orbitals F level. This is indicated from the abnormally low value of the third transition enthalpy of lanthanum, gadolinium and lutetium in their chemical behavior. In general, the earlier members of series are quite reactive, similar to calcium, but with increasing atomic number they have more like aluminum. Values for E0 for half reaction: Ln3 positive aqueous plus 3 electrons gives Ln solid, are in the range of -2.2 to -2.4 V, except for U, for which the value is -2.0 V. This is of course a small variation. The metals combined with hydrogen when gently heated in the gas, the carbides Ln3C, Ln2C3 and Ln C2 are formed when the metals are heated with carbon. They liberate hydrogen and from dilute acid and burn in halogens to form halides. They form oxides M2O3 and hydroxides MOH3. The hydroxides are definite compounds and just hydrated oxides. They are basic like alkaline earth metal oxides and hydroxides. Their general reactions are depicted in figure 4.7. Lanthanides is for the production of alloy steels for plates and pipes. A well-known alloy is mixed metal, which consists of a lanthanoid metal 95% and iron 5% and traces of SCCA and Al. A good deal of mixed metal is used in Mg-based alloy to produce bullet shell and lighter flint. Mixed oxide of lanthanoid are employed as gas catalyst in petroleum cracking. Some individual allen oxides are used as phosphorus in television screens and similar fluorescing surfaces. The actinoids include the 14 elements from Th to Lr. The name, symbols, and some properties of these elements are as follows. They are given in Table 4.10. The actinoids are radioactive elements and their earlier members have relatively long half-lives. The latter ones have half-life values ranging from a day to 3 minutes. Of fluoricium Z is equal to 103. The latter members could be prepared only in nanogram quantities. These facts render their study more difficult. Electronic configuration. All the actinoids are believed to have the electronic configuration of 7s2 and variable occupancy of the 5f and 6d subshell. The 14 electrons are formally added to 5f, though not in thorium. Z is equal to 90, but from Pa onwards, the 5f orbitals are complete to element 103. There are irregularities in the electronic configuration of actinoids, like those in the lanthanoids, are related to the stabilities of the F0, F7, and F14 occupancy of the 5f orbitals. Thus, the configuration of Am and Cm are Rn 5f7, 7s2, and Rn5f7, 6d1, 7s2. Although the 5f orbitals resemble the 4f orbitals in their angular part of the wave function, they are not as buried as 4f orbitals, and hence 5f electrons can participate in bonding to a far greater extent. The general trend in ionic sizes. The general trend in lanthanoid is observable in the actinides as well. There is a gradual decrease in the size of atoms or M3 positive ions across the series. This may be referred to the actinoid contraction like lanthanide contraction. The contraction is, however, greater from element to element in the series, resulting from poor shielding by 5f electrons. Oxidation state. There is a great change of oxidation state, which is a part of attributed to the fact that the 5f, 6d, and 7s levels are of comparable energies. The non-oxidation state of actinoids are listed in table 4.11. The actinoids show in general +3 oxidation state. The elements in the first half of the series frequently exhibit higher oxidation state. For example, the maximum oxidation state increase from +4 in Th to +5, +6, and +7 respectively in Pa, U, and Np, but decreases in succeeding elements. Table 4.11. The actinoids resemble the lanthanoids in having more compounds in +3 state than in the +4 state. However, +3 and +4 ions tend to hydrolyze. Because the distribution of oxidation state among the actinoids is so uneven and so different for the former and the later elements, it is unsatisfactory to review their chemistry in terms of oxidation state, general characteristic, and comparison with lanthanoids. The actinide metal are all silvery in appearance but display a variety of structures. The structural variability is important due to irregularities in metallic radii, which are far greater than in lanthanoids. The actinoids are highly reactive metals, especially when finely divided. The action of boiling water on them, for example, gives a mixture of oxide and hydride, and combination with most known metals take place at moderate temperature. Hydrochloric acid attacks all metals but Most are slightly affected by nitric acid owing to the formation of protective oxide layers. Alkalis have no accent. The magnetic properties of the actinoids are more complex than those of the lanthanoids, although the variation of the magnetic susceptibility of the actinoids with the number of unpaired 5f electrons is roughly parallel to the corresponding result of the lanthanoid. The latter have higher values. It is evident from the behavior of the actinoids that the ionization enthalpy of early actinoids, though not accurately known, but are lower than for the early lanthanoids. This is quite reasonable, since it is to be expected that when 5f orbitals are beginning to be occupied, they will penetrate less into the inner core of electrons. The 5f electron will therefore be more effectively shielded from the nuclear charge than the 4f electrons of the corresponding lanthanoids. Because the outer electrons are less firmly held, they are available for bonding in the actinoids. In comparison of the actinoids with the lanthanoids with respect to different characteristics, as discussed above, reveals that behavior similar to the lanthanoids is not evident until the second half of the actinoid series. However, even the early actinoids resemble the lanthanoids in showing close similarity with each other and in gradual variation in properties which do not entail change in oxidation state. The lanthanoid and actinoid contraction have extended effect on the sizes and therefore the properties of the elements succeeding them in their respective period. The lanthanoid contraction is more important because the chemistry of the elements succeeding the actinoids are much less known at present time. Some application of D and F block elements. Iron and steel are the most important construction material. Their production is based on the reduction of the iron oxide, then the removal of impurities and the addition of carbon and alloying metals such as chromium, manganese and nickel. Some compounds are manufactured for special purposes such as TiO for the pigment industry and MnO2 for the use in dry batteries, as the battery industry also requires Zn and NiCd. The elements of group 11 are still worthy for being called the coinage metal, although Ag and Au are restricted to collection items and the contemporary UK copper coins and copper coated steel. The silver UK coins are a CuNi alloy. Many of the metals and or their compounds are essential catalysts in the chemical industry. V2O5 catalyst the oxidation of SO2 in the manufacture of the sulfuric acid. TiCl4 with AlCH33 forms the basis of a Ziegler catalyst used to manufacture polyethylene. Iron catalysts are used in the Haber process for the production of ammonia from N to H2 mixtures. Nickel catalyst enables the hydrogenation of fat to proceed in the Walker process. The oxidation of ethine to ethanol is catalyzed by PdCl2. Nickel complexes are useful in the polymerization of alkynes and other organic compounds such as benzene. The photographic industry relies on the special light sensitive properties of HBr. Summary: the D block consisting of group 3 to 12 occupies the large middle section of the periodic table. In these elements, the inner d orbitals are progressively filled. The F block is placed outside at the bottom and the periodic table, and in elements of this block 4f and 5f orbitals are progressively filled corresponding to the filling of 3d, 4d and 5d orbitals. Three series of transition elements were recognized. All the transition elements exhibit typical metallic properties such as high tensile strength, ductility, malleability, thermal and electrical conductivity, and metallic character. Their melting and boiling point are high, which are attributed to the involvement of n-1d electron, resulting into strong interatomic bonding in the many of the properties. The maximum occur at about the middle of each series, which indicates that one unpaired electron per d orbital is particularly a favorable configuration for strong interatomic interaction. Successive ionizations enthalpy do not increase as steeply as in the main group elements with increasing atomic number. Hence, the loss of the variable number of the electrons from n-1d orbitals is not energetically unfavorable. The involvement of n-1d electrons in the behavior of transition elements impact their distinct characteristics to these elements. Thus, in addition to variable oxidation state, they exhibit paramagnetic behavior, catalytic properties, and tendency of the formation of colored ions, interstitial compound, and complexes. The transition elements vary widely in their chemical behavior. Many of them are sufficiently electropositive to dissolve in mineral acid, although a few of the are noble of the first series, with the exception of copper. All the metals are relatively reactive. The transition metals react with a number of known metals like oxygen, nitrogen, sulfur, and halogen to form binary compounds. The first series is transition metal oxides are generally formed from the reaction of the metal which oxygen at high temperatures. These oxides dissolve in acids and bases to form oxometallic salts. Potassium dichromate and potassium permanganate are a common example. Potassium dichromate is prepared from the chromite ore by fusion with alkali in presence of air and acidifying the extract. Pyrolusite are or Pyrolusite or MnO2 is used for preparation of potassium permanganate. Both the dichromate and permanganate ion are strong oxidizing agents. The two series of inner transition elements, lanthanoids and actinoids, constitute the F block of the periodic table, with the successive filling of the inner orbitals for F. There is a gradual decrease in the atomic and ionic sizes of these metals along the series lanthanide contraction. This has far-reaching consequences in the chemistry of the elements succeeding them. Lanthanum and all the lanthanoids are rather soft white metals. They react easily with water to give solutions giving +3 ion. The principal oxidation is +3, although +4 and +2 oxidation state are also exhibited by someone. Occasionally, the chemistry of the actinoids is more complex in view of their ability to exist in different oxidation states. Furthermore, many of the actinoids elements are radioactive, which make the study of the elements rather difficult. There are many useful applications of D and F block elements and their compounds, notable among them being in varieties of steels, catalyst, complexes, organic synthesis, etc. Thank you.